So I'm Alex. I'm Alex from BigStep. This talk is going to be about the economics of scaling Cassandra. It's actually, we've had a set of analysis that we did for this particular talk. We did it for different technologies before, for Couchbase, Elasticsearch, and a few others. And the idea is that we want to understand how big data technologies scale, in the sense that how much money do I have to put in to get a specific level of performance, or vice versa. Because we all know that a lot of NoSQL databases scale horizontally, so they say, but the problem is that by adding an extra node, it doesn't necessarily mean we get twice the performance. So the question is, to which extent this holds true for a particular set of technologies. And today, this analysis is going to focus on Cassandra, or specifically data stacks. So we're going to go over a little bit about the way we did the benchmarks, about scaling horizontally, scaling vertically, a little bit about virtualization, and about Docker. And I would really love to make this a conversation rather than boring monologue. So please stop me at any time, raise your hand, and ask me anything. All right? Okay, so I'm Alex from BigStep, essentially a developer, and I've been product manager for about 7 years now, and I've been designing products for the hosting business ever since. If you haven't heard about us, we're an infrastructure as a service provider focused on big data and high-performance applications. That's all we do. We're essentially a bare metal cloud, but we are different than SoftLayer or Rackspace in the sense that we have compute nodes and storage nodes, and we boot the compute nodes from the storage nodes. And the storage nodes are all SSDs, and they're distributed across the entire network. There's no connection between them. We have a very fast, high throughput, and low latency network that uses cut-through switching. So we only look at the first few bytes of a packet before forwarding it to the appropriate port. So because of this architecture that we have, we can do stuff like cloning and snapshotting, and we can do it without any hypervisor. So essentially, you have pretty much the same flexibility that you have in virtualized environments, but with bare metal. So this means we're very good for essentially everything that it runs in memory. Because if you take virtualization out, you get a better performance level. And actually, I'm going to show you exactly how much you can gain, not necessarily on our platform, but in general on virtualized versus bare metal machines. We also partner and we deploy a lot of other technologies like Datameer, Elasticsearch, Splunk, and we've done a lot of benchmarking with them to try to understand what happened. So essentially, we like to say about us that we are like the fastest cloud in the world. I know it's a bold statement, but we are willing to put that to the test. Right, so as I said, we have been doing a lot of testing to understand the technologies, and also because it's quite cool to play with them. And also, we have this constant recurring question coming from our clients. How many nodes do I have? I have this amount of data. How many Cassandra nodes do I need? Or how many Couchbase nodes do I need? How many Hadoop nodes? How much memory and stuff like that? And we have to be prepared to answer those questions. So let's get into the more techie stuff. The benchmarks that we did were done on fairly big machines with 192 gigs of RAM. The target ones, the ones that actually hold the data, are 192 gigs of RAM. The other ones are 128, both of them with dual socket configurations, very, very fast CPUs, and 10 gig networks, essentially two 10 gig networks in parallel, one for the RPC, the other one for the regular traffic. We use CentOS. We use DevSHM. So essentially, instead of using a disk, we used memory because we wanted to really drive the performance without benchmarking the disk. So we used DevSHM, and we had about 100 gig free on them. We again did a little bit of optimizations with IRQ balance and disabled transparent huge pages. And we use jmeter instead of the Cassandra's built-in benchmarking tool. We've written a custom sampler for jmeter. Have you used jmeter before, by the way? Anyone? All right. Oh, cool. So we've written our own custom sampler that uses the Java driver. We did that because we wanted to make sure that we could at least compare a little bit between this technology and other technologies. And also, I want to make sure that I get to experiment with something that the client would have. Anyway, we'll get back into more details later on. So what we did essentially was we inserted about 10 million records into Cassandra and got them back, and then changed every one of them. So it's essentially we're doing 3 operations. It's insert and select and update on those records using 2,000 concurrent connections from all the 8 machines. So a lot of JVMs there working. And essentially this is what we got. Now, the absolute figures are not necessarily important, although they are quite fast. I mean, those are milliseconds, and there are milliseconds for the entire data set, and 2,000 concurrent connections, so single-digit and 2-digit milliseconds. But what you have to remember here, and this is the latency test, is that if you compare running the same test on one node versus the one with 2 nodes, for instance, in the insert system, you do get, you reduce half the time it takes to insert, right, from 19 to 10. But if you add an extra node, you're not reducing that a whole lot. Again, for 4 nodes, it actually increases, and the same happens for select and updates, right? So again, one extra node not necessarily it increases performance, but not necessarily doubles it. The same is for throughput. And the throughput actually is amazing. We got up to 250,000 operations per second with this cluster of 4 nodes, which is very good. And we pretty much see the same, the same ratios. The insert benefits a lot more than the selects in adding extra nodes. But again, you're not necessarily doubling. As you see on the insert side, you add some extra node, and the more nodes you have, the less efficient you are in the way you're increasing your performance. Okay, so keep that in mind for a second. Now, scaling vertically, essentially we are comparing 2 instance types that we have. One is the 4.32, which essentially it has 4 cores and 32 gigs of RAM, it's a smaller one, to the one that has 20 cores and 192 gigs of RAM. And there is an increase, right? It's almost, you would say, twice the performance for the bigger one as opposed to the one with 32 gigs and a single CPU. Again, you have to remember this a bit. So twice the power. And now, in order to really understand how that translates into money, we did what we call an analysis of performance to price ratio. And in order to get a feeling of performance, we had to have like this composite metric out of all the other metrics that we got. And we ended up something like this. And we divided it to the price of that particular configuration. And long story short, it looks like this. So essentially what this tells us, and by the way, this is identical, or I mean, it looks the same for other technologies as well. It looks the same for Couchbase, looks the same for Impala, looks the same for all the NoSQL technologies out there. You have this curve that drops, which tells you the more nodes you have, the less efficient you are in the way you're spending your money, unfortunately. So actually the best placed configuration is the one that has the smaller CPU and less RAM, because that one costs about £0.5 per hour, and the next one, the one with 192 gigs of RAM, costs about £2 per hour. So it's 4 times more expensive, but only twice more performant. So hence, it has a better price to performance ratio. Right. Now, why does this happen, you might be asking? And some of you already know about Amdahl's law, and maybe some of you already know about the hardware prices. So the Amdahl's law essentially tells you that regardless of the technology that you use, you'll always have something in common, something that can be parallelized, because the no problem is, embarrassingly parallelizable. And so, yeah, you will not be able to parallelize completely. And the other one is the hardware prices. Now, this happens for every component, but the CPU is easily verifiable. There's this website which is called the CPU Mark, which rates, benchmarks all the CPUs on the market and rates them, right? And you can also find the prices for the particular CPUs either on an Intel site or on that particular site. And if you take all the CPUs in this E5 family and you try to plot them and do something like, hey, if I have a CPU which costs twice, will I have twice the amount of power? And of course, the answer is not by far. Apparently, the more power the specific CPU has, you get like an exponential increase in price, right? So, for instance, for 10K, whatever that is, it's a 10K mark for the E5263, it costs about $600. And for about twice that much, for the E52670, it costs $3,000. So it's a huge change in prices, and the same happens for every other type of component in a PC, in a server. All right, so this is essentially how money spending efficiency looks like. You're best off using a single node. If you can't use a single node, because you shouldn't use a single node, don't try to overkill it with too big machines. Try to keep the size of the machines small enough, and also don't try to overdo it with the number of machines. Try to keep the number of machines to where your sweet spot is, right? Now, let's move over to the virtualization impact on big data applications. So there's a tool that you can download and install. It's called Sysbench, and you can use it to read and write 1 terabyte of data to and from memory. And you get something like this on a virtualized host versus a native one. And this is on the latest hardware that we could find. And the reason is, and I'm going to get lower level a bit, and I hope you don't mind, is because if you ever written any C application, you know that number that you work with pointers is not necessarily, it's not an actual address in memory. It's actually a reference to the virtual memory address space, right? So every process has its own virtual memory. Now, in order to do this translation between the virtual memory space and the actual physical space, the CPU and the operating system work together to do this translation. And this translation, native, if you would do it badly enough, it would have to have at least two requests to memory in order to actually access one memory. So essentially, it would double your latency to the memory. So of course, it doesn't happen this way. And operating system have implemented something which is called pages or memory pages, which are segments of continuous memory blocks that can be allocated to applications. The typical size for a page is about 4K. Now, in order to do the translation between the same translation but to the pages, the operating system maintains something which is called a page table, right? And a page table has about 32 bits, and it does a translation between physical memory and the actual virtual memory. Now, the problem with this approach is that if you have, as I said, a page is 4K long. So to map a 4 gig memory segment to these pages means that your page table should have 4 million divided by 4K is about 1 million entries. So for every 4 gigs of RAM, you have to have like 1 million entries in the page table. Now for 40 gigs of RAM, again, you have 10 million entries of 2 bytes. So the page table grows bigger and bigger and bigger. And in order to, whenever you have to access memory, you would have to look up this entire page table and do the translation, which is not efficient. Now, in the 70s, a solution has been introduced to this, which is called the TLB, right? The translation look-aside buffer. And this is essentially a fourth cache in the CPU, which helps the CPU do the translation without looking into the entire page table. Now, I know it's a lot to take in right now, but I'm getting somewhere. So the problem with the TLB is that whenever you hit the TLB, it's fine. You do the translation, the CPU does the translation for you, and it's very, very fast. But whenever you hit something which is not in the TLB, and by the way, the TLB's typical size is about 200 entries, which is very small in comparison to the amount of RAM that we currently have, you do something which is called a TLB miss. And a TLB miss incurs a penalty which is proportionate to the size of the page table. Now, normally about 150 cycles, and this is on bare metal. So we are hugely inefficient for applications that use, do a lot of random reads. And guess which applications have the highest TLB miss ratio in the world? There's a study done by Intel, which is called Memory System Characterization for Big Data Workloads. It's fairly new, and I encourage you to read it. They analyzed Hadoop tasks and NoSQL applications to see which ones have the highest TLB miss ratio, and they did something even more amazing. They put some chip between the actual motherboard and the memory DIMM to record the traffic. This is a very interesting study. You should read it. This is like 2 excerpts for it. Apparently, NoSQL applications have the highest TLB miss ratio because they have like random read patterns. Right. Now, the problem with this is that when virtualization came along, you had like a virtual to physical memory translation, so it's a third level of indirection, which of course blows up every performance benefit that you would get from a regular TLB cache. Now, and that's why the first implementations of virtualization software like QEMU were like incredibly slow. Now, people thought about this and tried to solve the problem of 3 levels of indirection, and did something which is called shadow page tables, which essentially you would use directly. You're not doing a virtual to physical translation, but just rather a virtual to physical translation directly from the virtual memory to the actual CPU. Now, that's good, but when you do context switching between virtual machines, and you do one VM to another VM, and you have to flush the entire TLB because it doesn't make sense for another VM. One VM has, a state, and the other one has another one. And whenever you flush the TLB, you get like a huge performance penalty. You have to rebuild the TLB, or at least repopulate it. So that didn't work either. So now they have this technology which is called the VTX. By the way, the other one was still VTX, but another version. This VTX technology, what happens is it modified the entries in the TLB cache so that they have an additional byte that you can identify which VMs, to which VM that particular entry belongs to, so you don't have to flush everything out every time you do context switching between VMs. But the problem with that is that TLB misses now incur like 12 times more time to rebuild that particular entry because it's a lot more complex to build a TLB cache. So essentially, they sacrificed a particular type of applications and a particular type of memory access patterns to get performance for smaller applications that use smaller space. And this is something which is documented on VMware as well, on Intel and other solutions. Essentially, it's a trade-off. So it's now, whenever you have a high TLB miss ratio, it's actually a lot more dramatic. You get even less performance from virtualized environments for big in-memory applications such as Cassandra or Spark, for that matter. So long story short, I encourage you to avoid virtualization if you can. Now, there are solutions to, if you want to have something else, and of course, Docker is one potential solution, not necessarily covering the same area as virtualization, but for certain it could help you. And we did a benchmark on this as well. I want to make sure, because people say that Docker is native speed, We want to make sure if that's the case, and we did the test by running, a native node and a native node with one Docker container running the same, the same benchmark in it, and with 2 containers and 4 containers. And apparently, it's a bad idea to run multiple containers on an already saturated node, which, of course, I could have thought about it before I did. Anyway, so you do get a bit of performance penalty with Docker. I don't know yet why. We did a lot of optimizations. We run the Docker container in privileged mode. I think it's because of the additional routing that has to happen in the machines. But it's there. I mean, it's almost at the same level. You get about 21 versus 19 milliseconds for the inserts, 18 versus 19, so almost barely noticeable, especially in, when you're not driving the CPUs to, close to 100%. So I encourage you to use the Docker if you have to use something. Now, this is the throughput. This is how the throughput looks like. It's pretty much the same story. Now, the conclusions are, Cassandra is actually very fast. The only thing that was faster in some particular workloads was Couchbase, but you can't really compare the two. But again, Cassandra is very fast, especially, I mean, it was fast on reads as well. People usually associate Cassandra with writes, write performance and write in general, but it's very good in reads as well. I've also tested the in-memory feature that has been, recently introduced, and it gets to pretty much the same numbers as I have here because, remember, I use DevSHM. But the problem with the in-memory option of DataStax is that it's limited to 1 gig. So if you have to use table which is bigger than 1 gig, you can't use a out-of-the-box in-memory section, at least right now, because it runs on in heap. So you would also get a lot of garbage collection related issues. Maybe later on it could work, or you could do what I did with DevSHM. Now, use Docker if you want. There's not a problem, but don't try to use more than 2 containers. Again, the more nodes you add, the less efficient you are in the way you're spending your money. But we haven't taken into account IOPS and disk in general. And that's very, very much platform specific. So depending, and workload specific. And if you have like a very write intensive or read intensive IOPS bound application, of course, you might want to consider looking at the disks a lot more. But that's a different, separate discussion. Now, again, the bigger the nodes, the less efficient you are on performance to price ratio. But if you need the increase performance for that particular node, maybe reducing latency across the entire platform, go for those. Yeah, and we will try to do a few more tests on the disks. So that was it. I was quite fast. Do you have any questions? Raise your hand. Okay, please, Matt.
When you did the Docker testing, did you try isolating
Oops, sorry.
each Docker container to, say, the NUMA domains of the machine?
No, I haven't done any NUMA pinning for the Docker containers, but I know that Cassandra does it natively anyways. So, right. So I think because we had NUMA CTL installed, it comes with IRQ balance. Oops, where was it? So it should have worked, but you're right, I haven't checked to see if they do NUMA pinning. By the way, for those of you who don't know what NUMA pinning is, do you know? Okay. So NUMA pinning essentially means that there is something which is called a QPI link between 2 CPUs, and one CPU has a memory controller, and the memory DIMMs, get controlled essentially by that particular CPU. And if you have a process that tries to access memory, because from the operating system's perspective, you have like one contiguous block of memory. But when you have a process running on one CPU that has to access memory from another CPU's memory DIMMs, what happens is that you have to traverse this QPI link. And we did tests previously, and there's a talk on O'Reilly that I did that explains how the QPI link affects performance. But the idea is that whenever you're doing this cross QPI link memory access, you're like at least doubling the latency of the memory access, if not like 4 times slower. So I've seen occasions, if you do that memory test with the sysbench that I've been showing you, you can get actually on a 2-socket machine, you can get way lower performance in accessing memory than you do on a single-socket machine, except if you do NUMA pinning, which essentially means that there's this utility called NUMA-CTL, and there's a daemon called NUMA-D, which you can use to pin a process to a specific NUMA node. NUMA stands for non-uniform memory access. It's the architecture of multi-socket machines. So whenever you do pinning, you will only access memory from that particular node. So you get a lot more performance. And happily enough, Cassandra does it automatically if you have NUMA-CTL installed, which is a great thing to have. And by the way, I also encourage you to use something like IRQ balance, because by default, operating systems don't distribute the IRQs, the interrupts. Whenever you have like network interrupts coming from the network card, you're just blocking a single core by default. So there's this tool called the IRQ balance, which balances the IRQs across the entire set of cores that you have in order to get faster performance. And also there are driver stacks for the network cards, which can be used to move access from the kernel space to the user space. So you're not doing context switching between the kernel space and the user space. And apparently that really pumps up performance because you're not using interrupts anymore. You're using like a pull model or event-based model, if you like. And it increases your performance on the network side, lowers the latency, reduces the CPU usage. So it's better. Any other questions?
How easy is to install such a class that when you're expecting, I don't know.
Can you please repeat that?
So if you have virtual machines, it's generally much easier to deal with your hardware. How easier is when you have to deal with firmware?
So if you use like this new generation of cloud providers like us, which essentially provide you with pretty much the same level of flexibility, like you can do, as I said, you can do cloning. You can hit a button and in 10 minutes you get up and running the instance, and then after 10 minutes you shut it down. You have access to the actual physical machine via a KVM-like interface. You get to see the screen of the server if anything fails. So there's this new breed of cloud providers which come along and try to solve this problem of performance penalties induced by virtualization, but giving you pretty much the same level of flexibility. So I can't say for certain that it is exactly the same level of flexibility. For instance, what you can't do right now, you can't do like live migration, right, between hosts with physical machines. Actually, we're working on that. But right now, there's no way of doing live migration. You have to do like restarts or reboots. But what you can do, though, is you can do upgrades. So you can do your machine, if you have like 192 gigs of RAM now, if you want to switch to another box with like 256, you can do just a restart and reboots on another machine. So essentially, what happens is that the virtualization layer tends to move towards the hardware lower and lower. I mean, the things that virtualization accomplishes now will be done in hardware later on anyways. And but not in the sense that it will help the software do this, but rather the hardware itself will enable virtualization-related paradigms to happen. And we already see server providers that automate servers with REST APIs. So you can work with the server as you would with a virtual machine, or you could use us or somebody like us. Any other questions? Now is the time. Okay.